In the last video, we talked about our Hindu Arabic system of numbering, which was a positional base 10 system. So the 10 tells us where we group, and the position of a digit tells us the value in that place. So a base system is a system where you use a certain number to start regrouping. And if it's positional, then the first power for us is 10 to the 0 power, which gives us our ones place. 10 to the first power gives us our tens place. 10 squared gives us our hundreds. 10 cubed gives us our thousands, and so forth. So you can see that we have powers of 10 starting with 0 going up as we go further to the left. Now, this base could be something else. We could have a base 5 system if we, or someone may actually use a base 5 system. So this would be 5 to the 0 power, or the ones place. 5 to the first power, or the fives place. 5 squared, or the 25s place. 5 cubed, which is the 125s place, and so forth. Okay, so depending on what the base is, and there are a lot of different base systems that can be used, what we have is just an increasing power of that same base. Now, I said earlier in the last video that we have a base 10, so we have 10 digits, 0 through 9, and we regroup every time we get past 9 to the 10th place. We go to the next place value. And this kind of shows you a little bit of how the system evolved. And if you recall, I said that we used a Hindu Arabic system because the Hindus were the first to come up with how to represent the numbers. They came up with the positional system, and then the Arabs were the ones who translated that system to Europe, and where we got our system from. Now suppose I use a different base. The binary numeral system uses a base 2, and that's what computer languages, at the very base of all computer languages, they have a binary code. And it's binary because really all the code is telling the machine to do is on or off at a certain place on the microchip. So here now the base is 2, but we use the same powers. Okay, so we have, just let me write this down here and we'll go back to the example. 2 to the 0 power, or our ones place. 2 to the first power, our twos place. 2 to the second power, which would be in this case our fours place. 2 cubed, which would be 8, and so forth as we go. So this number, if I wanted to find its base 10 equivalent, I would write it in expanded form with 2 as the base. So if I count over here, I'm in the 8th position. Since we start at 0, this is 2 to the 7th place. 2 to the 6th, 2 to the 5th, and so forth. So what I have here is a 1 in the 2 to the 7th, and I have a 0 in the 2 to the 6th place, a 0 in the 2 to the 5th power place, a 1 in the 2 to the 4th place, a 1 in the 2 cubed place, 0 in the 2 squared place, 1 in the 2's place, and then 1 in the 1's place. So I find out what 2 to the 7th is and multiply it times 1, so that happens to be 128. And then of course I have 0 here. And my next one I have 0. 2 to the 4th is 16 times 1, so that gives me 16. And then I have 2 cubed times 1, which is 8. And then I have 2 squared times 0 plus 2 plus 1. And when I add those together, I get the base 10 representation of this. And you can think of the base 10 blocks we looked at. If I wanted to draw base 2 blocks, then I'd have a unit block, but I start regrouping at 2, so my long would be 2 units long. My flat would be 2 of these put together, so it would be 4. My cube would be 2 of the flats put together, which would give me, and this is not going to be a pretty drawing, but if you can picture putting those two together, I'd have 8 cubes all together here. So that kind of gives you an idea of how this would work. Another base is the base 16 system. It's called hexadecimal, hex 6 decimal 10. Now we only can represent the digits 0 through 9. So in order to get more digits up to represent 16 different digits, we add on 6 letters from our alphabet. So if I wanted to look at this number, D80, okay, so the 0 is in the 1's place, it's 16 to the 0 power. Then I have 8 in the 16 to the 1st power, and I have a D. So D corresponds to 16 to the 2 power. Okay. Now D, for us in a base 10 system, if I count up here, I go 0 through 9, 10, 11, 12, 13. So D represents 13 in a base 10 system. So I would have 13 times 16 squared plus 8 times 16 to the 1st power plus 0 times 16 to the 0 power. And I add those together and I get the decimal equivalent, or the base 10 equivalent of this hexadecimal system. So the idea is the position matters, and the position reflects a power, and the base reflects where you're regrouping. Now let's look at the Mayan numeral system. It's also a positional system, and it has a base 20. So the first, if we wrote it left to right as we write, we'd have 20 to the 0 power, 20 to the 1st, 20 squared, and so forth. Okay, except they didn't write their numbers from left to right. They wrote them increasing as you go up. So this was their 1's place, and then this was their 20's place, and this was their 20 squared or 400's place. And you can see their numbers got quite large. So these are the digits the symbols they used for their digits. And the amazing thing about the Mayans is they were the first culture in history to actually have a symbol for zero. Having a symbol for zero gives you a place where you can go up to the next place value. If you don't have a zero, which we'll see, there are systems that didn't have a zero, there's no way your base could be giveaway positions. But it's this thought of a zero, and that's just a big break in math history, just a good thing that happened. And it was now the Babylonian numeral system had a base 60, so they had to have 59 different symbols, and then they could write the next place. Now, if it was zero in a position, they would just write a blank instead of not putting a number there. Okay? But then it's hard to tell where there's a blank and where there should be a space between things, so it's really hard to learn how to use it. But it's a base 60, and that would be very difficult, I would think. 10 representation. Another one, because it's really interesting to see how math has developed in different cultures throughout time. An octal system. Okay, in some Native American tribes, they didn't count their actual thumb and fingers; they counted the spaces between. So, where would they start recounting? What would be their digits? So they have a base 8 system. Because at 8, you start all over again on the next hand. Finally, we'll look at the Roman numeral system. So the Roman numeral system can't really be considered positional, because if you wanted to write 20, you just write 2 X's, right? You could write 3 M's to represent 3,000. But you always do write it from largest number, or largest digit, I guess you would say, to smallest. And then you add them up. But the one case that doesn't hold is if you start reading down and you're using your larger numbers, and then all of a sudden you write a smaller number before a larger one. That doesn't indicate adding them together. That indicates taking the number in front away from the number behind it. So here I would have M is 1,000, D is 500, C is 100, L is 50, X is 10, V is 5, and then I have 2 ones. So in base 10, that would be 1,667. And I know to add those together because I didn't have any place where I switched between a smaller and a larger. I kept going down in size. Now this CLIX, so I start with a C, it's 100, L is 50, I shouldn't come next, right? Because the X is worth more. It's 10. But what this tells me is I need one less than 10. So that'd be plus 9, which turns out to be 159. So it's not really positional, but if you switch the order in which it's written, then you go from adding to subtracting. And if you ever look at copyright dates, like at the end of a movie or different things like that, um, they're always written in Roman numerals. The Olympics, their numbers are always written in Roman numerals. And so we see them all the time